Our next topic is light. We are going to talk about what light is. The technical term for light is electromagnetic radiation, or the spectrum over which electromagnetic radiation exists. So this literally is just light. And so I said electromagnetic radiation. So does that mean light is radiation? And the answer to that is yes. You are being pummeled with radiation right now, a phenomenally large amount of radiation. Obviously, you're not being harmed by it. You've been hit by this your entire life. There is a chance every time you get hit by one of these things, every time you get hit by some radiation, you could have a problem. But for the most part, radiation cannot harm you. In the same way that none of you should be fearful of your screens on your phones or the screens that you're looking at on a computer to watch this. The light that's coming out of there is not dangerous to us. So we usually think about radiation being, something from nuclear bombs or some kind of laser gun or something of that nature. And in essence, it's just light. And light is, it comes in lots of different types, a lot of different flavors per se. All right, so electromagnetic radiation is called electromagnetic radiation because it has two fields, an electric field and a magnetic field that are perpendicular to each other, and then they travel in one direction. So this is a good image of what it is that we're talking about when we're talking about light. So again, this is all types of light. There are a couple of things you can measure with light. One of them is pretty easy. It's called the wavelength. The symbol for the wavelength is this, it's called lambda. It looks like an upside down cursive Y, and it's a Greek letter, and we have it again up here. And so the wavelength is just literally the length of the wave. Most people measure it from crest to crest, but you could measure from trough to trough, or where it's going down across the axis to where it's going down across the axis again. Any of those spots show you the distance of one full wave cycle. I started at the bottom, I go all the way up, and then I come all the way to the bottom. I start in the middle, I go down, I go back up, and then I come down, and I'm right where I was before. Or I'm at the top, come down, and now I'm back up at the top. So each of those will measure a wavelength, and each of the different types of light that exist based off of their wavelength. So those types of light would be like visible light, infrared lights, X-rays, gamma rays, radio waves, microwaves. All of those are different types of light. And the difference between them, in essence, is how far apart those waves are. If they're close to each other, or if they're further from each other, they have completely different properties. The unit that we use, it totally depends on the wavelength. It could be a really small wave, I have to use nanometers, or it could be a really big wave, and I have to use meters or kilometers. Yes, waves can be a kilometer long. The other way to talk about it is something called frequency. And frequency's symbol is going to be this cursive V. It's actually a Greek letter called nu, N-U, lowercase Greek letter nu. And so let's look at these options here. We've got wavelengths. And so we've got red, orange, yellow, green, blue, and purple. And all of these have different wavelengths. But also we have high frequency and low frequency. So you can see the things down here, the shorter waves have a higher frequency, and the longer waves have a smaller, a larger frequency. The longer the wave, the shorter the frequency. So if I'm talking about frequency, I'm talking about something that happens per unit time. So let's say that this is, 1 nanosecond. So how many waves are there? 1, 2, 3, 4 of the purple. There's only maybe 1.5 of the blue. There's about, a little more than 1 of the yellow. There isn't even a whole wave of yellow that fits. And orange, not a whole wave, and red, not a whole wave. So you can sit in one place and count the number of waves that go by in a second, and that would tell you your wavelength is. If I'm talking about light, that frequency is a huge number, like 10 to the 19th. So what is that? This is like looking like a mole, right? All right, so 1,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,0 in 1 second. So that's happening because they're really, really fast. You usually think about frequency in terms of what comes out of the wall socket, and that comes out at 60 hertz per second. Or if you're looking at two different phones, like an iPhone and an iPhone Pro, one of the differences between those is the frequency at which the screen refreshes itself. So does it refresh 120 times per second, 90 times per second, 60 times per second? And the more times it refreshes, the shorter your battery life is going to be, but the clearer the image is going to be. Imagine those flip books. If you flipped it really slow, it's obvious that you're looking at individual images. But if you flip it really fast, then it kind of looks like a moving object. So high frequency is associated with short waves, and low frequency is associated with long waves. So their relationship is inverse of each other. And you can talk about it in either direction. It doesn't matter. The visible spectrum is all the colors of the rainbow put together, and we end up seeing white light out of that. Let's talk about most of the spectrums. There are subspectrums inside of here, but we have radio waves, microwaves, infrared waves, visible light, ultraviolet, X-rays, and gamma rays. And so two ways to think about this. The wavelength in meters. So this is 1,000, there are radio waves that are a kilometer long. And this is 100 hundreds of meters long, or tens of meters long, or a meter, or a decameter, or a centimeter, or a millimeter, and they just keep getting smaller. Micrometer, nanometer, femtometer. So these things get really, really tiny. The other way to think about it is the frequency. So what their frequency is, relatively low to relatively high. Inside of these different things, like inside of radio waves, you've got the frequency at which cell phones operate, frequency at which old like walkie-talkies operate, or old phones, the cordless phones that you might have for a landline, if anybody still has landlines. There are radio waves for things like, what just happened to the screen? That was weird. There are radio waves for like avalanche beacons, and those are really long waves. And there are radio waves for like CB, for cars, like police and fire to talk to each other, or radio waves for like submarines to talk. And those are all like radio waves that are really, really long. They travel very far distances, and not much interacts with them. Okay, so you can see that what we can see, there's a lot of different parts of the spectrum, right? I go from 10 to the third all the way 10 to the negative 12th. So that's 15 orders of magnitude. And an order of magnitude is 10. So 15 different times I can multiply by 10, and I have different sizes of these wavelengths. The wavelengths for visible light are actually pretty darn small. 10 to the negative 6th, that's somewhere between 10 to the negative 6th and 10 to the negative 7th. That's going to be, we'll get a little more specific about that, but these things are super small. And you can see that what we can see of the visible spectrum is tiny. All we had is this right here. I've got all of this stuff on this side and all of this stuff on this side, and we can't see that with our eyes. We absolutely have devices that can detect those things, but we physically can't see those things. We could feel those things. There could be some heat involved with those, but to actually see those things, we would not be able to do. Okay, so I want to be super, super clear about something that a lot of people are not clear about. So again, we talked about this being radiation, and radiation can be dangerous. And I said that some of the radiation is dangerous, but most of the radiation you're getting hit by right now is not dangerous. So here's the line of demarcation of dangerousness, right there. That's the line. Anything over here, dangerous. Anything over here, not dangerous. So what constitutes danger? For me, what would constitute danger in the way we think about radiation being a bad thing is that danger would mean that it could cause cancer. It could disrupt a cell and cause cancer. To cause cancer, you would need to take a carbon atom connected to another carbon atom, and you would need to break that bond. This takes a significant amount of energy. It takes a significant amount of energy to break a carbon-carbon bond. You should know that because those trees that you see outside are being exposed to radiation constantly. They're almost completely contained within carbon-carbon bonds. What is happening to them as they sit out there? Nothing. The radiation isn't doing anything to the trees. They're actually absorbing the radiation and sustaining themselves with that radiation. So to break a carbon-carbon bond, what you need is radiation that has more energy than a carbon-carbon bond. And that happens at ultraviolet. So we understand that because we wear sunscreen. We wear sunscreen so we don't get burned by ultraviolet rays that come from the sun. X-rays and gamma rays also come from the sun, but they're blocked by the atmosphere. And it's the ultraviolet rays, some of them get through. Some X-rays and some gamma rays do get through, but it's very, very small amount that actually make it through our atmosphere. Most of them just get basically deflected and shot around the exterior of the planet. But some ultraviolet rays can make it through to us, and that's why we need to protect ourselves from that. So it's important for us to realize that the short wavelengths, can't spell, about just short, wow, I super can't spell. The short wavelengths have more energy. There's another line here called electron, photon energy of electron volts, 10 to the 6th electron volts versus 10 to the negative 9th electron volts. Again, 15 orders of magnitude difference between those things. So this is the point right here. If I'm somewhere between 1 and 10 electron volts, closer to 10, I have the ability to break a carbon-carbon bond if I'm a type of radiation. So ultraviolet light can come in, UV can come in and break a carbon-carbon bond. When that happens, that could cause cancer. I'm not saying it will, I'm saying it could cause cancer. Most of the time when you get a sunburn, you just have broken bonds and those cells die. And that's what that redness is, cells that are being killed. And then your body has to come over and replace those things. Every once in a while, some of those cells, instead of dying, they mutate themselves and turn into cancer. So everything over here, no, cancer. Can't cause cancer. It is not possible. So let's be super clear about one thing. This is cell phones. That's where cell phones operate. So how far are cell phones away from being able to cause cancer? Well, let's say that the cancer causing happens at 10 to the negative 7th as far as wavelengths goes. And these cell phones, their size is about 10 to the 1st. So the difference between that is 8 orders of magnitude. So what's 8 orders of magnitude? 1, 2, 3, 4, 5, 6, 7. There we go. 10 million. So cell phone radiation is 10 million times too weak to cause cancer. So those crazy people who think 5G is going to cause cancer or cause COVID or whatever, they're crazy. And they're being told something and just blindly believing it. It's not possible because that radiation doesn't have enough energy. If you're going to be scared of cell phone radiation, you should absolutely be scared of visible light because visible light is 7 orders of magnitude more powerful. So you need to go down into the dark. But that's not going to be good enough because infrared radiation is the radiation that's given off by heat. So if you've got a stove that's giving off radiation, And that's somewhere between 4 and 7 times more, orders of magnitude more than cell phones. So you should definitely be afraid of that if you're afraid of cell phones. So really, ultimately is you shouldn't be worried about cell phone radiation. You should only be worried about putting on sunscreen and staying away from nuclear bombs and staying away from X-ray machines, because this light down here can't cause any harm. So what else is down here? I said infrared. That's literally the heat that comes off of your stovetop or your oven, which obviously you're not afraid of getting cancer. You're not going to touch it. Like, these things can be dangerous if they're in magnitude. Don't turn your stovetop on and say, hey, my chemistry teacher said this radiation isn't going to hurt me, because it can kill the cells, but it's not going to be able to cause cancer. Same situation with a microwave. It can kill you if you're given enough energy. Think about it like this. If you got hit with a baseball, I don't know, in the stomach, that's not going to kill you, even if you're being hit by the person who throws a baseball absolutely the hardest. I've seen 109 miles an hour. 109 miles an hour baseball won't kill you. But what if you got hit by 1,000 of them? That would probably kill you. So same situation. Don't get exposed to too much of those radiations. Otherwise, you could be killed simply by blunt force. Okay, so infrared, that's just the heat signature of light that's given off. And microwaves, those the cool thing about microwaves that we learned was microwaves. Here's the water molecule. And water molecules vibrate in and out. The hydrogen is sort of like a slinky. The H's and O's vibrate in and out. And when that happens, there's a certain frequency at which they do that. And microwaves match that frequency. So if you've got water inside the microwave, it will cause the resonant frequency of the H and the O's to vibrate more rapidly. And so if I'm increasing the speed of a molecule, I'm increasing its temperature. So the water molecules are moving faster and faster and faster, and that causes your food to heat up, simply because the water inside the food is heating up faster. Okay. That's probably good for this. Again, different types of radiation that we've got are radio waves, and these radio waves are the range for radio waves is huge. You've got AM and FM radio in there that people don't necessarily listen to all that much, but more importantly, we've got cell phone radiation in there. We've got Wi-Fi radiation in there. We've got walkie-talkies and CDs, all that kind of stuff. All of that is inside of the radio wave genre. Okay, so we just talked about microwaves and how they increase the speed of water molecules, increasing its temperature. Infrared waves, those are going to be the heat that comes off of something. So stovetop, oven, even like you, coming off of you. If somebody's using night vision goggles, they're most likely using infrared goggles. And so the goggles receive the information and they see different amounts of heat. So if it's nighttime and everything's cool except for a cat that you're looking for, the cat will show up as red, and then you will go off and grab that cat because you now can see it. Only because the computer has converted the infrared light into visible light for you. And then visible light, the visible spectrum is between 400 nanometers and 750 nanometers. So this is a very, very small sliver of the whole spectrum. Nanometers are 10 to the negative 9th. So 10 to the negative 9th meters, that's pretty darn short. And so red light, this red has less energy than your violet light over here. And again, we've got sorry, that's not yellow. Let's do this. Orange, yellow, green, blue, and violet. And so that's Roy G. Biv, and there's your rainbow. That's where the Roy G. Biv thing comes from. Ultraviolet lights, we need to make sure that that gets blocked. And right now it's being blocked for us by the ozone layer. And we talked about ozone before. It's three oxygens connected to each other, and one side's connected with a double bond. And when the UV light comes in, it breaks this bond, and then the oxygen and this extra oxygen reform with themselves. So it's a self-healing shield for us for ultraviolet radiation. X-rays, those have substantial penetrating power, which is why we're looking for broken bones or problems with inside of somebody. We use that, but we can't use gamma rays because the gamma rays would end up causing too much damage to the person. And this usually, this is something that would be generated by a nuclear bomb. So if you're killed by regular radiation, electromagnetic radiation, it could be that you got hit with too much gamma rays. Another thing associated with waves is amplitude. Amplitude really doesn't have anything to do with the energy of a specific photon of light or one wavelength of those lights. Amplitude is more like how many of them are hitting you. So that there aren't really variations in heights of the wave. Really what amplitude means with radiation is the more amplitude is the more waves that you've got floating around. And I'll talk about two different calculations. So the calculations, well, actually three different calculations. Calculations are going to be how I convert from a wavelength to a frequency and then back from a frequency to a wavelength. And here's the equation where c is the speed of light. Yes, that E equals mc squared speed of light. And this is that nu or frequency, and this is lambda or wavelength. So their inverse relationship generates this equation. So if you got a question, like, let's go back up here for a second. Okay, so let's say we're going to talk about 600 nanometer orange light. So what's the frequency of 600 nanometer orange light? All righty, give myself some space. So I'll go 600 nanometers. Okay. And I'm going to go 10 to the 9th nanometers is 1 meter. And doing that allows me to cancel out my nanometers. Okay. And then I've got oh, I did this upside down. That's fine. Let me start over. Let me start over with the way I would want to start this. That makes more sense for me. So 3 times 10 to the 8th meters per second. I'm starting with the speed of light because my answer needs to have units of 1/seconds because I'm measuring events per second, and the event I'm measuring is number of wavelengths that pass by a point in 1 second. Okay, so I have the second unit where I want. So then the next thing I'm going to do is I'm going to write 600 nanometers. Those things can't cancel out. So I'll write 10 to the 9th nanometers is 1 meter. All right, so now I can take meters and cancel meters out, and nanometers and cancel those out. And then I'm going to end up with, let me do the math on this, 3E8 divided by 600 times 1E9. And so I get 5 times 10 to the 14th hertz, or inverted seconds. And so there's my frequency, and you can see that's a lot. The number of orange wavelengths that pass by 1 point in 1 second is 5 times 10 to the 14th. So 10 to the 12th is a trillion. So this would be 50 trillion of these things pass a point in 1 second. Obviously, that's a lot. If you were given the frequency, so I've got an example here. Well, I'll just pick something. Let's go with 7.5 times 10 to the 11th 1/seconds. So I got this number, and I want to know what the wavelength of this is going to be. Okay, So I want wavelength with this. So I'm going to start my calculation with 3 times 10 to the 8th meters per second. Why am I doing that? Because I want a distance in the numerator, and now I've got a distance in the numerator. So I want to get rid of this seconds. So I'm going to get rid of seconds by writing 7.5 times 10 to the 11th, and then seconds goes in the numerator here. And that way I can cancel out the seconds. And then my math on this is going to be 3E8 divided by 7.5 E11. And I got 0.0004. The other way to write that would be 4 times 10 to the negative 4th meters. Okay, so let's look on our spectrum. What's 10 to the negative 4th? Where would that be? 10 to the negative 4th. So we would be looking at infrared, possibly the end of the microwave spectrum. Okay. The other calculation we can do is how much energy these things have. And so the energy equation, we have 2 equations for that. I could use either one of these. If I have the frequency, I could use this one. If I have the wavelength, I can use that one. And so they both have technically, they both have the speed of light built into them, but the thing that is new about this is h, which is Planck's constant. So last time we talked about Planck being one of the people who came up with quantum mechanics, and one of the things that he came up with was this constant. And look at this number. It seems kind of insignificant, 10 to the negative 34th, but it's one of the most fundamentally important constants in all of science. Okay, so let's do that 600 nanometer orange light. Let's see how much energy that thing has. All right, so I've got I want energy. I want a value of energy when I'm finished with this. So I'm going to do 6.626 times 10 to the negative 34th joules times seconds. Why did I start with that? Because that's an energy unit in the numerator. So now I need to get rid of that seconds. So how am I going to get rid of that seconds when I've got 600 nanometers? Well, I'm going to use the speed of light. So I'll put 3 times 10 to the 8th meters per second. And doing that allows me to cancel out my seconds unit. Okay, great. I still have this length unit, and I need to get rid of that. So I'm going to put 600 nanometers here. And I need more because I can't cancel meters and nanometers out without a conversion. So 10 to the 9th nanometers is 1 meter. So now that I've done that, I can get the meters to cancel out, the nanometers to cancel out. And then let's see what my number is. So 6.626 E negative 34 times 3E8 times 1E9 divided by 600. And I get 3.3 times 10 to the negative 19th joules. Again, that's a super small number, negative 19th joules. So each individual wavelength of light has a very small amount of energy. But when you get hit with light, you get hit with so many of them that they add up. Like being hit with 1 grain of sand, no big deal. But if you're down on the sandbar on a 30-knot day, then you're getting pummeled by lots of sand, and now it becomes painful. All right, that's all I have for today for this video.